So this is question 8 of the sample assessment materials, paper 3. So throughout this question, I and J are unit vectors east and north, respectively. So we've got a radio-controlled model boat on the surface of a large pond. It's modelled as a particle. At time t = 0, the boat is at fixed point O and is moving due north with speed 0.6 meters per second. Relative to O, the position vector of the boat at time t seconds is r meters. At time t = 15, the velocity of the boat is 10.5 I minus 0.9 j meters per second, and the acceleration of the boat is constant. So part A wants us to show the acceleration of the boat is 0.7 I minus 0.1 meters per second squared. So we know that acceleration is the change in velocity with respect to time. So if we know that the change in velocity is 10.5 I take away 0.9 j at t = 15, and at time t = 0, it's moving north, so that's 0.6 j, because j is the unit vector due north. So the change in velocity is 10.5 I take away 0.9 j take away 0.6 j. If I simplify that, I get that is 10.5 I take away 1.5 j. So the change in velocity is that. The change in time then is 15 seconds. So it's going from t = 15 there, t = 0, difference is 15. So A is the change in velocity divided by the change in time. So 10.5 I take away 1.5 j divided by 15. So that is 0.7 I, and that is negative 0.1 j meters per second squared. And double check that's what we wanted to get in the question, so we know we've got it right. Now, part B wants us to find R in terms of t. So R is the position, and we know that that is ut plus a half at squared. So figuring out what we've got, we know that A is 0.7 I take away 0.1 j, because we've just shown that. And we know that U, our initial speed, is 0.6 j. Okay. So if I substitute those in here, R is equal to 0.6 jt plus a half 0.7 I take away 0.1 j t squared. And it wanted us to find it in terms of t, so that's the answer to that part of the question. And part C wants us to find the value of t when the boat is northeast of O. So if it's northeast, we know that the I and the j components are equal in the position. So if we go back to our expression from part B and set the I components equal to the j components and solve it for t, we should be able to find our answer. So 0.6 jt plus, I'm going to expand this, 0.35i, take away 0.05 j t squared. Now I'm just going to rearrange this so that I have the coefficients of I together and then the coefficients of j together. So the I has 0.35 t squared I, and then the coefficients of j, we have 0.6 t, take away 0.05 t squared j. Now the coefficient of I is equal to the coefficient of j if its position is directly northeast. So that means that 0.35 t squared is equal to 0.6 t, take away 0.05 t squared. So let's just rearrange that and subtract 0.35 t squared, both sides. And then I'm going to factorize. And the solutions of that are either that t is equal to 0 or 0.6 take away 0.40 is equal to 0. And that gives me that t is equal to 1.5. So this is the solution that we're interested in. So t is equal to 1.5 in part C. And then part D wants us to find the value of t when the boat is moving in a northeast direction. So this time we're dealing about when the boat is moving. So we're thinking about its velocity. So v is equal to u plus at. Now u, the initial velocity, is 0.6 j. And then a, from earlier on in the question, is 0.7 I minus 0.1 j t. Now, if it's moving in a northeast direction, then the I and the j components are going to be equal. That's not northeast. That's northeast. So if we rearrange this so that we have the I and the j components, the coefficients of them together, we get 0.6 take away 0.1 t j plus 0.7 t I, and it's when this is equal to this. So the velocity moving that way is equal to the velocity moving that way. So 0.6 take away 0.1 t is equal to 0.7 t. So let's add 0.1 t onto both sides. So 0.6 equals 0.8 t, and then divide by 0.8, gives us 0.75 seconds. So the value of t when the boat is moving in a northeasterly direction is 0.75 seconds.